Given question, find slope equation and deflection equation for simply supported beam carrying uniformly distributed load W per unit run over a whole span by using double integration method. Solve one problem. In this video, we are going to find out slope equation and deflection equation for simply supported beam carrying uniformly distributed load over the whole span by using double integration method. If we observe the diagram, then the uniformly distributed load is given W per unit run and this total length of this beam is given L. If we observe at ends A and B, the beam is simply supported. We will first draw the free body diagram. We have to first show the reactions at point A and B in vertically upward direction. So these reactions are RA as well as RP. Now what is the total load? So total load is equal to W multiplied by L. Now this total load acts at the center of the beam AB. So we will select here one center point and we will select the total load that is equal to WL. And it is acting in the downward direction at the center. So we have to write here total load is equal to WL. Now if we observe, the beam is supported at two ends and therefore this total load is equally distributed at end A as well as B. So we can say that RA is equal to RB is equal to WL by 2. Now we will consider any section XX at a distance x from this RA. So I will show here the section XX. And the distance from the reaction RA is equal to x. Now we know that from this end A up to section XX there is uniformly distributed load whose value is W per unit run. That means what is this total load? That is this W multiplied by this length x. Now this load acts at the center of the in between A and this section XX. So we will select the center point and we will show the load. So load is equal to W into x. Now we will show the distance. So this distance from the end A and the section XX, that is equal to x by 2. So we will show here. Here is x by 2 and this is x by 2. I will show RA here. Now next step we have to find out bending moment at section XX. So we will take the summation of the moments from this left hand side. So how to find out? So if we observe, here is the reaction RA. Now if I move the compass about section XX in the direction of RA, then here is the clockwise direction. Now we will consider sign convention. For the clockwise direction we will use positive sign and for the anti-clockwise direction we will use negative sign. So how to write this bending moment? So this RA is equal to WL by 2. So we will write this force multiplied by distance and this direction is in the clockwise direction. So I will use positive sign. So WL by 2 multiplied by x. Now if we observe, there is second force which is in the downward direction. So if I move the compass about the center XX in the direction of WX, then there is anti-clockwise direction. So we will use negative sign. So minus this WX into this distance x by 2. So we will simplify this WX square by 2. WX square by 2. So this is the equation, that is the bending moment at section XX. I will write here the equation number 1. Now we know the formula for bending moment at any section. So bending moment at any section mx is equal to EI d square y by dx square. So this is the equation number 2. Now if we observe the left hand side for these two equations is same, so I will equate these two equations. Therefore EI d square y by dx square is equal to WLX by 2 minus WX square by 2. So this is the equation number 3. Now to find out slope equation as well as deflection equation, we are going to use double integration method. So here we will take the integration for this equation. So if I take the integration on both sides, so I will write here the next step is integration on both sides. So here for left hand side it will become EI dy by dx is equal to, now if we observe here is x as well as x square, so I will show here one formula. So here integration of x raised to n is equal to x raised to n plus 1 divided by n plus 1. So this is the common formula we have to apply for every time. So here is x raised to 1. So for x raised to 1 means it is equal to x square by 2. So I will write here WL. Now instead of x I will write x square by 2. So here in the numerator x square and here 2 multiplied by 2 4. Now in the same way for x square, here is x cube by 3. So here minus w. Now in numerator instead of x square we will write x cube and divided by 3. So 3 multiplied by 2 6. And we have to also show constant of integration. So this is the first integration. So I will write constant of integration as a C1. When uniformly distributed load is applied WL at the center, then the beam is deflected in this way. Now we will find out the value of constant of integration C1 by applying boundary conditions. If we observe, here is the length L by 2, that is this is the center point, and if I draw tangent to this curve, then here is the horizontal line. That means we can say that at length L by 2, here there is slope is equal to 0. Now if we observe equation number 4, then this dy by dx is nothing but slope. So at x is equal to L by 2, dy by dx is equal to 0, and these are the boundary conditions. So we will apply boundary conditions in equation number 4, and when we apply we will get the value of C1 minus WL cube by 24. So when we put the value of C1 in equation number 4, then we will get the equation number 5, and this is known as slope equation. So by using this equation we can calculate the slope at any point. So this slope equation is EI dy by dx is equal to WL x square by 4 minus WX cube by 6 minus WL cube by 24. So I will make the bracket to this equation. Now this dy by dx is known as slope at any point. Now we will find out the slope at point A. So if I draw tangent to this curve at the point A, then here is the slope at point A, and we will measure the slope in terms of angle theta, that is theta A. Now at A, if we observe at point A, x is equal to 0. So we will put x is equal to 0 in equation number 5, and dy by dx, that is the slope at A. So we will get minus WL cube by 24. So theta A is equal to minus WL cube by 24 EI. So this is the formula we will get the slope at point A. Now how to find out slope at point B? So I will draw here the tangent at B. Now if we observe, we measure the angle of theta A from this beam towards the slope in the clockwise direction, and here if we measure the angle, it is in opposite direction, that is in anti-clockwise direction, and this angle is theta B. So we get the angle theta B is equal to, so we have to just change the sign. So this minus sign we have to convert into plus and magnitude will remain same, that is plus WL cube by 24 EI. Now we will calculate deflection integration. We will take integration on both sides of the slope equation. So we will get EI dy by dx, that is y, is equal to WL by 4 is constant. Now what is the integration of x square, that is x cube by 3 minus w by 6 x raised to 4 by 4 minus WL cube by 24 x plus C2, where C2 is the constant of integration. Now we will simplify this. So EIy is equal to WL x cube by 12 minus Wx raised to 4 by 24 minus WL cube x by 24 plus C2. Now what is this y? So y is the deflection. Now if we observe this diagram, at point A, deflection of the beam is 0. And at point A, x is also equal to 0. So we will use this boundary condition. So at A, x is equal to 0 and y is equal to 0. These are the boundary conditions, and we will apply these boundary conditions in the equation number. This equation number I will write as a 6. In this equation number 6. So when we apply, we will get EIy is equal to, so when we apply this, we will get value of C2 is equal to 0. So when we put C2 is equal to 0, then EIy is equal to WL x cube by 12 minus Wx raised to 4 by 24 minus WL cube x by 24. Now this is known as deflection equation. So I will make the bracket. So we can use this equation to calculate the deflection, where y is the deflection. Now we will find out maximum deflection. If we observe this diagram, at the center there is maximum deflection, where I will show here the deflection, that means vertical distance from this original position. So this is C and this is C dash, and this is known as y max. So y max is equal to, so instead of y I will write y maximum, and instead of x I will write L by 2, because the distance from A to C is equal to L by 2. So when we simplify this, then we will get y maximum is equal to minus 5 WL raised to 4 divided by 384 EI. So this is the final formula to calculate maximum deflection. Now why minus sign? Because this deflection is in the downward direction. Find the slope and deflection at x is equal to 1.8 meter, where I is equal to 30 into 10 raised to minus 6 meter raised to 4 and E is equal to 200 giganewton per meter square. In this question, uniformly distributed load is given 3 kilonewton per meter and the length of beam 6 meter is given. If we observe, we have to find out slope at point C, where the point C is given at a distance x is equal to 1.8 meter. So what is the formula for the simply supported beam carrying uniformly distributed load? So we will write this formula. So this is the slope equation. Now this dy by dx is nothing but the slope, and this dy by dx we will write, that is at point C we will write here as a theta c. So we know that this slope we always measure in terms of angle. So angle at point C, that is known as theta c. So I will show here. So this is the point C. I will extend this point C in the free body diagram. So here is the original position of the beam, and when it deflects, it bends in this way. So if I draw tangent at this point, then this is known as slope. Now we have to find out this angle. So EI theta c is equal to WL x square by 4. So W is known 3 kilonewton. So we will write here as a 3000 Newton per meter. L 6 x square, that is 1.8 square divided by 4, minus W, that is 3000 1.8 cube by 6 minus WL cube by 24. So when we solve this, we will get minus 15,300. Now we have to measure only angle theta c, so we will divide it by E. That is the Young's modulus. It is given 200 giganewton per meter square. So we will convert it into Newton per meter square, that is 200 into 10 raised to 9. And this I, that is the mass moment of inertia, 30 into 10 raised to minus 6. So when we calculate this, then we will get this angle in terms of radian. So we will convert it into degree by multiplying with 180 by pi. So here we will get the answer with negative sign. So this is minus 0.146 degree. Now we will calculate deflection at point C. So we know that deflection, that is, this is the original position C and here is the final position C dash. So this vertical distance C to C dash is known as deflection at point C, that is YC. We have formula EIY is equal to WLX cube by 12 minus WX raised to 4 by 24 minus WL cube x by 24. Now if we put y is equal to yc, then we have to put x is equal to 1.8 and L is equal to 6 and this W is equal to 3000 Newton per meter. So when we put these values, then we will get the answer minus 41164.2. Now we have to find out deflection at point C, that is YC. Therefore YC is equal to, we will divide this value with EI, where E is the Young's modulus and I is mass moment of inertia. So these values are mentioned in the question. So when we calculate this, then we will get the answer minus 6.8 into 10 raised to minus 3 meter. Now this negative sign indicates that the deflection is in the downward direction. So here is the original position and this is the final position, and because of the negative sign, the deflection is in the downward direction.